section 6.2, directional derivatives and the gradient vector. For functions of two variables, z equals f of xy, the partial derivatives f sub x and f sub y represent the rate of change of z in the x and y directions. That is, directions of unit vectors I and j. In this direction, it will be f sub x. In this directional derivative will be f sub y. Now, it would be nice to be able to find the slope of tangent lines to the surfaces in the direction of an arbitrary unit vector u equal ab. So consider an arbitrary direction u, and along the direction we want to find the slope of the tangent line. Okay, here that's the concept of the directional derivatives. The directional derivative of f at x0, y0, in the direction of unit vector u is defined in this way. Okay, this quotient is measured in the direction. Okay, for this inside of a parenthesis, we can write this one in this way. That is x0 plus h and u. In u direction, h distance is here considered, and that is now x0. Right? So in u direction, we try to find the slope. Once the limit exists, then we say that is the directional derivative of f in u direction. Okay, that's the definition. Now, for the numerator, here we may subtract this term and add this one. And now we try to deal with this 2 and that 2 separately, so that the quotient is the same as, now divided by h and multiply a and a here. The same a for these two terms, divided by h and also divided by b and multiply b here. Okay. Now, if we look at the quotient as h approaches 0, then we can see quite easily. Okay, that one is the same, but here in x direction is perturbed, so that once it is x direction, okay, now for AB, that's x direction and this is AB, then this quotient is measured, okay, a little bit of perturbation in y. However, the direction is that direction. That direction, the slope is measured, and as h approaches, these two will convert to y0. So that eventually, this term, if the limit exists, then it will convert to f sub x directional slope. And for that one, but you can see quite easily, this whole thing is converting to f sub y because x0, and then now only the perturbation, the point is obtained in y direction, so that it'll convert to f sub y. So we can say that here this quotient will convert to a f sub x plus b f sub y as h approaches 0. Okay, so here we have a theorem. If f is the differentiable function of x and y, then f has a directional derivative in the direction of any unit vector u, a, b are components, and du f the directional derivative in the direction of u is the same as now f sub x times a plus f sub y times b. We collect here f sub x, f sub y, and ab. Then we can write down in this way. Okay, this one, this vector with u dot product. Later on, we'll define this one as the gradient vector. So we'll use the notation. But anyway, right now, we have this conclusion. Okay, let's see this example. F of xy is defined in this way. Find the directional derivative duf when u is the unit vector given by the angle pi over 4, and what is duf at 2, 3. Okay, so here in the beginning you may try to get the direction. There is a 45 degree direction, pi over 4. So that is unit vector in the direction is cosine pi over 4 and sine pi over 4, which is this one, 1 over square root 2 in x direction. In y component, the same. Okay, that is the direction. Now, if we try to use the formula, then we have to get f sub x, f sub y evaluated at 2, 3. Okay, let's try to get f sub x. X derivative for that one. There's a 3x squared. And now that is 2y. And that will be 0. And f sub y, y derivative, which is now, this will become 0 because we consider x as a constant. And that one will be 2x, right, that's 2x, and this one is 4 times y to the 3. Now we set the point 2 and 3. X is 2, y equal 3. Okay. Then from this one, x equal 2, then is 12, and y equal 3, 6, so that is 18. Now, for f sub y, x equal 2, then that is 4, and y equal 3, then here that is 3 times 3, which is 81. Now, 81 times 4, right? Oh, no, it's 27. I'm sorry. 27 times 4, so that is 68, right? Okay, times 4, 27 times 4, now 68, 108, here, 108, so it is 1/12. Okay, so du of f at 2, 3 is the same as this vector 18 and 120 and dot product with u, which is 1 over square root 2 and 1 over square root 2. So that is same as 1 over square root 2 and addition, that is 130. So we may write this one. We multiply square root 2, then now half of that one is 65 and square root 2. That's the final answer. Okay. Okay. For this one, you may try yourself and try to get it. Now, for this one, angle is pi over 3, which is 60 degrees. So that u must be here. First component is cosine of the angle, which is 1/2, right? And then now second one, the sine pi over 3 is square root of 3 over 2, right? That is unit vector. So now exactly same way you can finish this problem. Now the concept of directional derivative can be defined for functions of three variables. In fact, functions of arbitrarily many variables. Okay. Now here f is defined as a function of three variables x, y, z in this way, and find the directional derivative of f at 1, 3, 1 in the direction of v 2, minus 1. Let's try to decide the unit vector in the direction. That must be u equal v over length of v. Okay, length of v is now, that is square root of the Euclidean length is 4 plus 4 plus 1, so it's 3. Okay, so here we have that is 1/3 of 2 minus 2 minus 1. That's u. Okay. Now we have to find f sub x, f sub y, f sub z, and evaluate it at here 1, 3, 1. Okay. Okay, f sub x, that is x derivative, that is 2x, and now y and z are considered as constant, so that we have that one. Okay, f sub y, y derivative, that is minus 4y, quite easily, and f sub z, which is now 4z cubed. Now we use the points 1, 3, 1, x is 1, y is 3, z is 1. From this one now there's 2, from this one minus 12, and from this one now 4. Right? So here the du f at 1, 3, 1 is same as the vector, that is 2 minus 12 and 4 with the dot product. Now that is 1/3, and here 2 minus 2 and 1. Yeah, that was quite simple. Now 1/3 constant, and this one is now 4 plus 24 plus 1. Okay. In fact, the last one is 4. Right? 4 plus 24, last one 4. Right? Okay, so you can finish the computation. Okay. Okay. Now here we'll define gradient vector. F is differential function of two variables, x and y. Then the gradient of f is the vector function given in this way. Just we are using the notation here, that is nabla f, and that is a vector of f sub x and f sub y. We may write in this way: I is 1, 0, j is 0, 1, so we can write in this way. Okay, that is called the gradient vector. For example, for that one, we can find the gradient vector easily. Just simply here we put x derivative, then that is cosine x, and plus, now that is y e to the xy, right? Now, if we do y derivative, then that'll be 0, and that is x e to the xy, right? Okay, so that is gradient, and we can get the value at 1 and 0, x, okay, 0 and 1, not 1 and 0. Okay, that is now 0 and 1, x is 0, y is 1, okay, let's see here. If x is 0, then it's 1. Y is 0, then that'll be 0. So that is, x is 0, then it's 1. Y is 1. 1, e to 0 is 1. So that 1 plus 1. Now, x is 0, so it must be 0. So that the vector is now here 2 and 0. And we can write this vector in this form. So we are using this angle notation when we try to write it in horizontally. Okay. With this notation of the gradient vector, here we can rewrite the directional derivative du of f, which is same as now gradient of f dot u. Right? So we'll use this one a lot for directional derivative. We consider this one most frequently. Find the directional derivative of f of xy given in this way at the point and in the direction of v 34. So first let's try to get u. U is now v over v length. From Pythagorean triple, we know that the length is 5, so that we have here now 5 and v, 3 and 4. That's the unit vector in the direction. Right? Okay, now f sub x and f sub y for gradient. Okay, that's x derivative as 2x y cubed, and that'll be 0. Now y derivative, that is 3x squared y squared and minus 4. That will make minus 4. And add 2n minus 1. Then x is 2, y is minus 1. X is 2, y is minus 1, so that there's a minus 4. And x is 2, y is minus 1, x is 2, 12 minus 4, which is 8. So here, the directional derivative df is same as gradient of f dot u. Okay, that is now minus 4 and 8, and dot, and 1 over 5, and here 3 and 4. 1 over 5 is constant, and we have dot product, which is minus 12 and plus 32. That'll be 20. So that the answer is 4. Okay. Now this is the major subject, maximizing the directional derivative. Okay, here duf, the directional derivative, can be written in this way: gradient of f dot u. By using a formula, we can write in this way: the length of gradient times the length of u, and cosine theta when theta is the angle between the gradient and u. Now length of u is 1, so we reach at that one. Now this value is maximum when cosine theta is 1, which means theta is 0, of which the maximum occurs when theta is 0. Quite easy, the result. Okay, so angle between u and gradient is 0, so same direction, then the directional derivative will be maximum. We say here in theorem, f is a differential function of 2 or 3 variables, then maximum, now we are taking maximum over u, and du f is the absolute value of length of gradient of f. Okay, here that is the maximum. So we can get here maximum. We are using here now absolute value sign, but it is basically the norm, Euclid norm. And this one occurs when U has the same direction as the gradient. Okay, so we already observed it from here. Well, let's see this problem. F of xy is x times e to the y. Find the rate of change of f at 1, 0 in the direction from P to Q. Okay, for this problem, let's try to find the U first. Okay, here, U is now the unit vector from now P to Q, right? So once V is given for that one, then unit vector will be obtained from that direction. How can we express that one? That is basically Q minus P. That is here, okay, there's minus 1 and 2, and P is 1 and 0. So that the vector is minus 1, minus 1, so that there's minus 2, and this is 2. Okay, and minus 2, 2 direction. So U, the unit vector in the direction, is now the length of that one is 2 square root of 2 divided by 2 square root of 2 is the same as 1 over square root of 2, and there's minus 1 and 1. Right? That is U direction. U, the unit vector. Now, we want to find the rate of change of f at 1, 0 for the function here. So start with gradient of f. This time we'll try to write down horizontally x derivative, that is e to the y, and y derivative, x e to the y. Now we are using here 1 and 0. X is 1, y equals 0. So that is 1, y equals 0, 1. X is 1, y equals 0. So again, that's 1. So the directional derivative is the same as here 1 and 1 and dot and 1 over square root of 2 minus 1 and 1. Okay, so here constant 1 over square root of 2, and this dot product is 0, so it is 0. That means that in this direction, the function is not changing, that's flat, if we consider only the direction. But it's not necessarily flat every direction. Okay. In what direction does f have the maximum rate of change? What is the maximum rate of change? From theory over there, the maximum of directional derivative. Now, we have to choose the direction so that it becomes maximum. That is happening when we try to choose the same direction of the gradient. So that means that if we choose here now u equal the same direction of that, which means 1 over square root of 2 and 1 and 1, then it will be maximum, but a maximum value is the norm of the gradient. So here we can easily say that maximum is gradient of f, the length, norm. So that is now already, this is 1 and 1, so that is square root of 2. Okay, so in this direction, if you choose u in this direction, then here there's maximum. This means that the gradient direction, the function is changing fastest. And that's the conclusion we want to get. Let's see here. if we choose u in the direction of gradient, the unit vector in the direction of gradient, then duf, which is gradient of f dot u, which makes now this dot product will make gradient of f norm squared. So one norm here, so one is cancelled. We recheck that on. This implies that the directional derivative is maximized in the gradient direction. So we can make a claim. The gradient direction is the direction where the function changes fastest. More precisely, increases fastest. Now, here, rather than change, we are using the word increases. Okay, that is along with some other mathematical analysis, the changes in fact the increase, but we may think in this way. Derivative is always increasing direction. Okay, let's start with the well-known function y equal fx. Okay, let's see here. And if y equal fx, then if this is y equal fx, the graph, then at the point, we know that it is increasing, so the slope over there is positive. For that one, the slope is negative, right? F prime is now positive, negative. Positive means that is this direction, negative means that direction. So derivative is always increasing direction. It is changing fastest, but gradient is increasing direction. So we can conclude that the gradient direction is the direction of fastest increase. Okay? That's the end of the section. Thank you.